Our universe is a place of immense wonder. It's filled with objects that defy imagination. Among the most fascinating are supermassive black holes. These cosmic titans lurk at the hearts of galaxies. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. Supermassive black holes are millions, even billions of times the mass of our sun. Imagine the sun squeezed into a space smaller than our solar system. That's the kind of density we're talking about. These objects are invisible to telescopes that detect light. However, we can see their effects on the surrounding stars and gas. These black holes are engines of incredible power. As matter falls into them, it heats up and emits intense radiation. This process, known as accretion, can outshine entire galaxies. Understanding these cosmic giants is crucial to understanding the evolution of the universe itself. They are not just destroyers, but also architects of the cosmic web we observe. To understand supermassive black holes, we need to journey back to the beginning. Imagine the early universe just a few 100 million years after the Big Bang. It was a vastly different place than the cosmos we see today. It was hotter, denser, and filled with a primordial soup of hydrogen and helium gas. Gravity, the architect of the universe, began to pull this gas together. Over millions of years, these clouds of gas collapsed under their own weight. As they contracted, they heated up, eventually reaching temperatures and densities high enough to ignite nuclear fusion. The first stars were born. These early stars were giants, hundreds of times more massive than our sun. They lived short, brilliant lives, consuming their nuclear fuel at a furious rate. When they eventually exhausted their fuel, these stars exploded as supernovae. These explosions seeded the early universe with heavier elements, the building blocks of planets and life itself. Some of these early stars were so massive that when they died, they collapsed under their own gravity. They formed stellar black holes, regions of space-time so dense that not even light could escape. These black holes, remnants of stellar death, became scattered throughout the early universe. But there's a problem. These stellar black holes are far too small to grow into the supermassive black holes we see today. Even if they consumed all the matter within their reach, it wouldn't be enough. They would need to devour the equivalent of millions, even billions of stars to reach such colossal sizes. And the early universe simply wasn't old enough for that to happen through normal accretion. This realization led scientists on a quest to uncover the origin of these supermassive black holes. How did these behemoths form in the relatively short time frame of the early universe? The answer, it seems, lies in a combination of factors, each more fascinating than the last. One intriguing possibility is the existence of primordial black holes. These hypothetical objects are thought to have formed in the extreme conditions of the very early universe, fractions of a second after the Big Bang. Unlike stellar black holes, which form from the death of stars, primordial black holes could have emerged directly from the dense energy fluctuations of the early universe. The idea is that if these fluctuations were dense enough, they could have collapsed directly into black holes. These primordial black holes could have had a wide range of masses, from minuscule to enormous. Some scientists believe that these primordial giants could have acted as seeds for the supermassive black holes we see today. However, there's a catch. We have yet to find definitive evidence of primordial black holes. They remain theoretical objects, and their existence is a subject of ongoing debate and research. While they offer a tantalizing explanation for the origin of supermassive black holes, we need more observational evidence to confirm their existence. Section 5. A cosmic collapse. A new theory emerges. Another theory suggests that supermassive black holes could form through a process called direct collapse. In this scenario, massive clouds of gas in the early universe collapse catastrophically under their own gravity. Unlike the formation of stars where nuclear fusion halts the collapse, these clouds collapse rapidly and directly into black holes. This direct collapse model bypasses the need for stars as intermediaries. It offers a way to form massive black holes in a relatively short amount of time. The key ingredient in this scenario is the presence of massive gas clouds in the early universe, pristine and devoid of the heavy elements that typically fuel star formation. This direct collapse model has gained traction in recent years as a plausible explanation for the existence of supermassive black holes in the early universe. It aligns with observations of distant quasars, extremely luminous objects powered by supermassive black holes. which suggests that these black holes formed rapidly in the early universe. Section 6. The Crucible of Creation, Gas Clouds and the Birth of Giants. The conditions within these massive gas clouds play a crucial role in determining the fate of a collapsing cloud. If the cloud is turbulent and fragmented, it's more likely to form stars. However, if the cloud is cold, dense, and relatively undisturbed, it's more likely to collapse directly into a black hole. Think of it like baking a cake. If you mix the batter too vigorously, you'll end up with a dense, crumbly cake. But if you mix it gently and let it rest, you'll get a light and airy cake. Similarly, the conditions within these gas clouds dictate whether they'll give birth to stars or to black holes. The presence of magnetic fields and radiation from nearby galaxies can also influence the fate of these clouds. Understanding these complex interactions is crucial to unraveling the mystery of supermassive black hole formation. Section 7. Cosmic cannibalism black holes on a collision course. Once formed, supermassive black holes don't just sit idly in the centers of galaxies. They continue to grow, fueled by the cosmic feast of gas and stars that surround them. This process, known as accretion, is a key driver of black hole growth. Imagine a black hole as a cosmic vacuum cleaner, drawing in everything in its path. As gas and stars spiral towards the event horizon, the point of no return, they heat up due to friction and release tremendous amounts of energy. This energy is what makes quasars, powered by supermassive black holes, some of the most luminous objects in the universe. But accretion alone isn't enough to explain the rapid growth of supermassive black holes in the early universe. Another mechanism is at play mergers. As galaxies collide and merge, a common occurrence in the early universe, their central black holes can also merge, creating even more massive black holes. Section 8. Webb's Cosmic Gaze, Unlocking Secrets from the Early Universe. The James Webb Space Telescope, humanity's most powerful telescope to date, is providing us with unprecedented views of the early universe. With its infrared vision, Webb can peer through the veil of gas and dust that obscures our view of the early universe, allowing us to witness the formation of the first stars and galaxies. Webb's observations are revolutionizing our understanding of supermassive black holes. It has already captured images of distant quasars, powered by supermassive black holes, shining brightly when the universe was less than 1 billion years old. These observations provide crucial clues about the formation and growth of these cosmic giants in the early universe. Webb is also allowing scientists to study the environments around supermassive black holes in unprecedented detail. By analyzing the light from these regions, scientists can determine the composition, temperature, and motion of the gas and dust swirling around these black holes, providing valuable insights into the physics of these extreme environments. Section 9. Uncharted Territories, the Future of Black Hole Exploration. The quest to understand supermassive black holes is far from over. As we continue to explore the universe with ever more powerful telescopes, we're bound to uncover new mysteries and challenge our current understanding of these cosmic titans. The future of black hole research is bright. New telescopes, such as the European Extremely Large Telescope, are currently under construction and will provide even sharper images of the universe than ever before. These telescopes, along with future space-based missions, will allow us to probe deeper into the early universe and unravel the secrets of supermassive black hole formation and evolution. The study of supermassive black holes is a journey into the most extreme environments in the universe. It's a testament to human curiosity and our desire to comprehend the cosmos and our place within it. As we continue to explore the universe, we're bound to make groundbreaking discoveries that will reshape our understanding of the cosmos and our place within it. The universe is full of wonders, and the adventure is just beginning.